final square. Beware. Like, you know, you get through the first two metrics.
Okay. If you get A or I can find it and then like on the midterms, you can get a 60 on that. As long as I just stay at
All right. Happy Friday. Let's spend today focusing on the solution to the Finn equation. And so we're going to do a quick recap of kind of where we ended last lecture. I know it was a bit of a rush with that derivation of the Finn equation, so we'll cover the last couple of steps there again so that we're all on the same page, and move on to how do we get the general solution and how do we actually use that to solve for some of the useful Finn metrics that we as engineers want to know. So we'll do that all through an example. So the solution to the Finn equation, right, or rather, sorry, recap of the Finn equation had us last time looking at, right, something that we call a pin fin. It doesn't necessarily have to be circular in cross section. It just has to. We're assuming that it's something sticking out of a base, some extruded surface, of which the cross-sectional area varies along its length. So we defined x as being the measure along its length, and we said that, right, if we took a slice through this thing, that had some cross-sectional area, AC, which varied along, which was a function of x. And so what we did was we took a little slice out of this fin. We said, assume we take a vanishingly thin slice of material, and we applied a first law analysis to this. So essentially we said, right, that there's some heat flowing in by conduction, some heat flowing out by conduction, and some heat leaving by convection. So we said Q, we'll call this Q conduction in, Q conduction out, and Q convection out. And so by applying this sort of this conservation of energy to this little plug of material, we said, you know, in words, heat conduction in minus heat loss to convection is what gives us the heat conduction out. And so by essentially applying Fourier's law to these heat conduction in and heat conduction out terms, along with a first order Taylor series expansion, and using Newton's law of cooling on this guy right here, what we arrived at was the general Finn equation, which states that the second partial derivative of T, or of temperature with respect to x, plus 1 over the cross-sectional area times the rate of change of the cross-sectional area times partial T, partial x, minus HP over K, A, C, T minus T, infinity is equal to 0. And so in this equation, right, AC is once again the cross-section area. P is the perimeter of that cross-section. H, right, is the convection coefficient. And K is our thermal conductivity. So relating this equation to sort of the word version up above, what we have is these first two terms give us the conduction in minus conduction out, and the second term gives us convection out. So all it's doing is bookkeeping. It's telling us that heat is flowing into this extended surface from the base, okay? And for every little length along that extended surface or fin, some of the heat is being shed by convection to the surrounding air, and the rest of it is being kicked on down the length of the fin. So previously, when we did the one-dimensional heat conduction, right, the idea was that the temperature between 2 points would vary linearly, right? If we were talking about Cartesian coordinates. In cases like this, however, because some of that thermal energy is being shed out the sides of our surface as it conducts down the length of the fin, we're going to end up with a temperature distribution that looks, at least we can take an educated guess, that rather than being linear is going to look something like this. It's going to be this sublinear behavior. Okay. So that's where we left off last time. Important to note, this is not the heat equation, but it's a cousin to the heat equation. The heat equation is still the end-all be-all of equations when it comes to conductive heat transfer. All right, I want to be clear about that. This does not replace it. However, the heat equation gets really messy when we start talking about multiple dimensions or weird geometries. So this is derived in the same way we used to derive the heat equation, right? First law applied to a little chunk of matter, but we've gone ahead and made some simplifications based on some assumptions that are peculiar to this pin sort of geometry. That is, we've assumed that one end is at fixed temperature. We've assumed that there is convective cooling all around the perimeter, and we've assumed that it is very long relative to sort of its thickness, if you will. So this, as I said before, this is given the special name, the fin equation. You could get the same thing, the same solution, by actually manually solving the heat equation in its more basic form. But we're going to save ourselves the trouble and work with what we've got here instead. So the version we're going to be working with today, and in fact the only one you're going to be expected to, the only case in which you're going to be expected to solve this by hand, is the case for a straight fin with a uniform cross-sectional area. So this might look like a circular fin. Alternatively, it could be a rectangular fin. Oops. Or really any other shape of fin is acceptable. The idea is that the cross-sectional area and the perimeter remain constant along the length of that fin, of that extended surface. So, right? So we can go ahead and say we've got P is a constant, and AC is also a constant along X, which again is defined along the length of that fin. So in this case, right, if we're assuming that both of those are constant on x, then our fin equation, which I'll go ahead and write one more time here, dx squared plus 1 over ac, dac dx t partial x minus hp over kac equal to 0. All right. Then this allows us to make some advantageous cancellations here, right? In its most basic form, if we don't make any assumptions about the cross-sectional area, what we've got here is that AC would change on x, P would change along x, and because of that, this becomes a second-order differential equation with non-constant coefficients, which is a pain to solve, I'll be honest. But if we make this assumption, then what we get to do is send that term off to 0, and assume that this term does not change along the length. So it takes it from a non-constant coefficient differential equation to a constant coefficient one, which everyone in this room has solved. We're also going to make a couple of advantageous substitutions. Rather than solving directly for t, we're going to install this dummy variable theta, which is defined as the difference between the local temperature and the ambient surrounding air temperature. So the idea is we're assuming that, right, we're going to assume that T infinity here is constant. Right, that we're assuming that the surrounding air is at uniform temperature, which means that then d theta dx turns into dt dx, and second derivative of theta with respect to x is d squared t dx squared. So that was substitution number 1. Substitution number 2 is just going to be consolidating this term right here. So we're going to define this variable. Oops, I want to make this distinct from the m I use for meters. We're going to call this m, but we'll give it sort of a script m. This is equal to the square root of hp over kac. So there's substitution number 2. Okay, if we plug both of these things into the equation above, right, it consolidates our expression into the simplified fin equation for constant cross-section, which is d squared or partial squared theta partial x squared minus m squared theta is equal to 0. So the advantage here, where we stand now, is that this is a dead simple equation in terms of differential equations. Have you guys taken vibrations at this point? No mechanical vibrations? All right, you'll get really comfortable with equations of this form and vibrations. This is essentially, well, it's analogous to when you solve a spring mass system. But anyway, from differential equations, do you guys know how you proceed to solve this? Essentially, you guess. You take an educated guess at the form of the solution. You say, well, I bet that theta has, suppose that theta x has the form of e to the ax, where a is some unknown constant, right? This is what's known as an ansatz, or a proposed solution. And so if we plugged this in, what we would find is that there's actually lots of different choices of A that work. And so what we find for our general solution, right? The general solution is the set of all possible solutions to this problem. We say that the general solution is equal, or theta x is equal to some constant e to the mx plus c2 e to the negative script mx. So in other words, we've said, well, if the solution has this sum form, we said that either a equals positive m or a equals negative m, either one of those would work. And so the solution can be formed from any combination of those two, which is why we end up with these two unknown constants, C1, C2. All right. What do we do to get C1, C2? Same thing we've been doing so far in the class, apply boundary conditions. Okay. So at this point, we can say, all right, it's got some logarithmic, some exponential temperature distribution. So we need to know something about the temperature, or something about the derivative of the temperature, or its second derivative. We need some information at two different points, or at least two separate pieces of information about the temperature in the fin in order to fully constrain this and turn it into a particular solution. One little trick we can play that makes our life easier before we apply that step is to recognize or to take advantage of hyperbolic functions, which say, in other words, we've got this idea that hyperbolic sine of mx is equal to e to the mx plus e to the negative mx over 2, and hyperbolic cosine of mx equal to e to the mx minus e to the negative mx over 2. So in other words, if we split up our C1s and C2s in particular ways, then we can sort of reorganize that general solution into one that is an alternative general solution. Theta of x is equal to C, we'll go ahead and say C3 cosh mx plus C4 sinh mx. So we've got these two sort of versions of our general solution, and they're actually completely equivalent. All right. If you were to say C1 is equal to some C3 plus C4, and C2 is equal to some C3 minus C4, right? C3 and C4 are just constants like C1 and C2. So you're turning your collection of two constants into the collection of two different constants, and if you regrouped everything, you would end up with this equation. The reason we like this is because we've got some nice identities that we should recall from like vector calc. We've got that, so I want you to recall that sinh of 0 is equal to 0, cosh 0 is equal to 1, x of sinh x is equal to cosh x, and x of cosh x is equal to sinh x. Which basically means that when we're like evaluating the temperature at the base, x equals 0, it's going to completely knock this term out. And if we're trying to evaluate something about the slope of the temperature, right? For example, try to evaluate a rate of conduction, then we essentially, our sinches and coches lend themselves very well to taking the derivatives. Okay, I'm going to keep that there for a second. All right, so as I said, our choices of C1, C2, or alternatively C3, C4 are defined by boundary conditions. And so what are these boundary conditions? Okay, we can sort of reason out what, yeah.
Would that be a negative sign?
Nope, not with hyperbolics. If we're talking about regular sine, cosine, yes. But these are even nicer to people doing calculus. So, boundary conditions. The first one, okay, which is almost universal to when you're working with fins, is that number one says, if let's say we've got right, we've said that where it's attached to its base, we've got some known temperature T sub B. This is a very frequent piece of information that you'd be given. Okay, is the temperature at the base of the fin. And so that gives us our first boundary condition, essentially that T at 0 is equal to TB, which means that theta 0 is equal to TB minus T infinity, which we'll just call theta sub B. All right? And then for our choice of, and so we can use that generally to solve for C1 or for C3 if we're working with our hyperbolics. But we'll do that again in, we'll actually put that in practice in an example here in a second. And so for the boundary condition number 2, usually we're going to specify that out here at the tip. The question is, what are we going to specify? So there are kind of 4 classic choices. 4 classic tip boundary conditions. The first, say A, is fixed temperature, where we would say essentially, come on, there we go. We'd say that T at L is equal to some T sub T, and we would turn that into theta sub L, or say, sorry, theta at L is equal to theta T. B is a convective boundary condition. Right? And just as in the case where we were solving the heat equation, this is essentially where we would place a very thin surface control volume at the tip of the fin there. We would say that the heat, essentially the heat entering that infinitesimally thin box due to conduction, has to leave by convection. So Q in equals Q out, in being convective or conductive heat transfer in, out being convective heat transfer out. And so this turns into negative K AT dx at x equals L is equal to H T T minus T infinity, or negative K theta dx at x equals L is equal to H times theta T. I don't know why my eraser's going so slowly there. All right. C is an insulated tip assumption. All right, an insulated or adiabatic tip. which essentially says that there's no heat transfer through the tip, meaning that there can be no temperature gradient. If there were temperature gradient, there would be conduction being pushed along by that temperature gradient. And so that says that dt dx at x equals L has to be 0, which again, putting into our dummy variable, says that d theta dx at x equals L has to be equal to 0. And finally, D is an infinitely long fin, in which case our boundary condition is less of a boundary condition and more of a limit. We say that the limit as x goes to infinity of theta x is to approach 0. In other words, as you go infinitely far down the fin, it eventually has to dissipate all of its excess thermal energy through convection and reach thermal equilibrium with the surrounding air. All right, which is a good approximation for fins that are very long. So between these four kind of classic tip boundary conditions, we have pretty much, we run the gamut of possible configurations for a cooling fin. So if you want, we're only going to talk about one of these in detail today, but you can find a summary of all of these in table 3.4 in the book. And then the section in which 3.4 is located has a good discussion of, right, what the physical reasoning for each of these boundary conditions is. So, okay, fine. We've summarized boundary conditions, discussed all these different configurations. Let's put it into practice with an example problem. It's all right if I scroll up here and get myself a clean screen. All right. So let's consider a case where we've got let's do that a little better. Let's assume that we've got some rectangular cooling fin with a uniform surface area. Okay, we'll say the thing is 5 centimeters across, 5 millimeters thick, and 30 centimeters long. It's attached to a substrate with a base temperature of 500 Kelvin. The surrounding air is at 295 Kelvin with a convective heat or convective coefficient of 10 watts per meter squared Kelvin. And let's say that we have attached a thermocouple to the tip of this bar, and we know that it has a tip temperature of 468 Kelvin. So when we're given a problem like this, it helps to kind of line up. Oh, and sorry, and I should mention that it is made of our favorite material, copper, which has a conductivity of 400 watts per meter Kelvin. Okay, so when given a problem like this, it helps to kind of list out the all the variables that we're going to call upon. For example, a sub c, p, and finally like that m parameter that keeps finding its way into our solution. So p, or the perimeter, right, is going to be 2 times 5 centimeters plus 5 millimeters. So 2 times 5.5, we're going to end up with an 11 centimeter perimeter, 0.11 meters. The cross-sectional area is going to be 5 centimeters by 5 millimeters. So 0.05 meters by 0.005 meters. It gives 2.5 times 10 to the negative 4th meters squared. Got H is equal to the 10 watts per meter squared Kelvin given above. K is equal to the 400 watts per meter Kelvin. And so taking all of these things together, right, that parameter script m, which is equal to the root of HP over KAC, is going to work out to a value of 3.321 per meter, or 1 over meter. So for this particular problem, we are likely to find it easier to apply, to work through the solution starting from the hyperbolic function form. Okay, we could do it from the e to the mx, e to the negative mx. That's fine. We'll end up with the same answer. But the hyperbolic function form is nice because, so we'll write this out. We're going to go and switch back to C1, C2, just for convenience. Cosh mx plus C2 sinh x. Okay, because when it comes time to apply our boundary conditions, we see number 1, which is that theta 0 is equal to Tb minus T infinity, or 205 Kelvin, right, because it's 500 Kelvin at the base, 295 Kelvin out in the ambient air. If we plug in a 0 into x in each of these arguments, the sinh goes away, right, because sinh of 0 is equal to 0, cosh goes to 1, and so we end up with equal to C1. Well, that's easy. We've got our first constant. So C1 is equal to this theta b 205 Kelvin. So we have this. Just for simplicity and to keep things from getting too messy, we're going to continue to write out the solution in symbolic form. So we'll call in this theta b. Applying boundary condition number 2. In this case, we've been given the temperature at the tip, right? 468 Kelvin. So we have that theta L is equal to theta tip, which is equal to T minus T infinity, which works out to, what's 468 minus 295? That's going to be 173. Yeah. 73 Kelvin. And so if we plug in L into x in each of these equations, or each of these forms, we'll end up with, right, theta L is equal to C1 is equal to theta b cosh ml plus C2 sinh ml is equal to this theta tip, right? So solving for C2, end up with C2 equal to theta tip minus theta b cosh ml all over cinch ml. And if we wanted to plug in our kind of individual values here, we'd find that, right, ml is equal to 0.995. The cosh of ml is equal to 1.537. Cinch of ml is 1.167. Here we've got theta at the tip. 468, 295. That is 176, or 173, isn't it? 68, 170 is going to be 73, 65. Yeah, it looks like I had a typo in my my example here. 173 Kelvin, and so this is going to work out to be and then theta B is equal to 205 Kelvin, right? So this is going to work out to be, got to recalculate this. 173 minus 205 times 0.537 all over 1.167. Okay, this is going to work out to a value of negative 121.75 Kelvin. So at this point, we've got C1, C2. We can just plug those into our expression for theta x. So theta x is going to work out to 205 Kelvin, cosh of 3.32 x per meter minus 121.75 Kelvin, cinch 3.32 x per meter. And that gives us our final temperature distribution. Or our temperature excess distribution, right? This is the difference between the ambient temperature in the air and the temperature in the rod. So if we want the actual absolute temperature distribution, right, we need T infinity plus theta x, which works out to 205 Kelvin cosh 3.32 x over meter plus that 295 Kelvin minus 121.75 Kelvin cinch 3.32 x over meter. Okay. Any questions at this point? So, we'll probably end up wrapping up the last couple of quick little things next time, but I want to quickly show you what this looks like, right? So, this means is we're going to start out, if this is x, oops, yeah, I'm supposed to be a black pen, x, here's our temperature, we're going to put TB out here, T tip. Our temperature distribution is going to look like this sort of decayed curve. And as I said before, the reason that it's not a straight line is because as the heat travels along by conduction, some of it's being dumped out to the surrounding air by convection. All right, so there's this decrease in the amount of thermal energy flowing. Okay, what about, so when we're using fins, right, the idea is that we want to use fins to dissipate some amount of additional thermal energy to cool something. It's the typical usage of extended surfaces. And so the real number that the engineer wants to know is how much heat is being dissipated. What is the heat rate being shed through those fins? The temperature distribution is fine. You can make sure that you're not melting anything. But what we really want to know is what is Q of the fin. Any ideas about how we would find Q of the fin? Kind of in broad strokes. All right, let's try any heat that's leaving the fin, right? All the net heat dissipation from the fin has to come in where? At the base, right, where it's connected to the wall. That's where all the thermal energy is entering. Okay? And by what mechanism is it entering the fin? Conduction. And we have the rate equation for conduction, right, in the form of Fourier's law. And because we have the temperature distribution, we can find the slope of the temperature at the wall and apply Fourier's law to find Q at this point. So in other words, QF is equal to negative K times T dx at x equals 0 times the cross-sectional area of the fin. Done. So once you have the temperature distribution, this becomes really, really simple. So for our solution up here, all right, we'll go ahead and leave it in this form. So for our fin that we just analyzed, this is going to be equal to negative 400 watts per meter Kelvin times the area, or we'll go ahead and write, times, the area, cross-sectional area of the fin, times the negative 4th meters squared, times, in this case, right, if we were to take the derivative of this, we would end up with dt dx, right, is going to give us basically C1 times m times sinh mx plus C2 come on, erase C2 m cosh mx. The reason this m comes out, right, is because chain rule, right? We're taking the derivative of cosh mx at m travels outside. And so evaluating this at 0, right, the idea is, again, 0, sinh disappears, and so all we end up with is C2 times m. So C2 in this case is our negative 121.75 Kelvin, and m is 3.321 meter. So plugging all of this in, we're going to end up with times 400 times 0.025 times 3.2, 40.42 watts. So this is typically what you want to know, right? That's the final, what the number all boils down to, or all the numbers boil down to, is how much heat can you actually shed through a given fin design. So solution process, right? If you encounter problems like this, there's one on the homework, right? I'm sure you've run into that, right? Start from the fin equation. choose the form of the general solution that you want, right? Choose the form of the general solution that you want to solve, whether that's the exponential form or the hyperbolic form. Okay, either one's fine. There we go. Determine boundary conditions. So you got to consider the problem. If they're given to you directly, great. If they tell you some information about the fin, you need to parse out that information and interpret what the boundary conditions need to be. Okay? If they say it's a fin that's just sitting out there in the air, and they give you a convective heat transfer coefficient and they don't give you the temperature at the end of the fin, guess what? You're going to have to apply a convective cooling boundary condition. If they say that the fin is really, really, really long, right, such that the end is at thermal equilibrium with the surrounding air, well, then you can apply the infinitely long fin approach. All right, so these are all things that come with practice. But once you determine the boundary conditions, find C1, C2, and then apply Fourier's law at tip to find Q flowing through the fin. So the last few little things I wanted to cover are how we often, like the kind of the simple ways people often describe the performance of fins. All right. So these are fin performance metrics. There are really two. Yeah.
Wouldn't we apply it at the base?
Huh?
Instead of the tip?
Oh, did I say tip? Oops, my bad. Yes, you'd apply it at the base. I spoke there. Okay. Thanks. Good catch. Okay, so fin performance metrics. The first one, and these are really simple. Hopefully these become pretty clear. The first one is what's known as the fin effectiveness. And in words, this is heat dissipation from fin relative to the heat dissipation from from the area on base if there was no fin. Okay, so thinking about this is what this boils down to is we take QF that we found divided by what would the convective heat transfer from the base area of the fin be if there was no fin at all. So it's the case of, right, fin on the wall compared to fin-sized blank area on the wall. All right, what's the heat transfer of these two cases relative to one another? So this works out to H times the cross-sectional area of the fin times, right? That's just Newton's law of cooling. This also works out to then Q sub F over H A sub C theta B. And this we give the variable name of epsilon sub F. So this is how we calculate the fin effectiveness. So in the case we just looked at, let's see, divided by 51.7. So in the case we just looked at, the fin effectiveness for the example above, epsilon f works out to a value of 78.9. So in other words, by adding the fin, we increase the amount of heat transfer, or the heat dissipation, by 79 times relative to if there was no fin. Right? So this is an indication of how worthwhile it is to even put a fin on whatever it is you're trying to cool. And the second one, which we'll conclude on, is it's known as the fin efficiency. I'll just give you the expression for this, and we can eta sub f. This is the heat transfer from the fin relative to the heat transfer from the perfect fin. So if A sub f is the total surface area of the fin, equals total surface area of fin, including the tip, right? So this is the lateral surface area plus the surface area of the tip. What this is saying is if the entire fin had uniform temperature equal to the base, if it were infinitely conductive, okay, the perfect conductor, then how much heat transfer could it shed? And so in this case, once again, we're dealing with 40 divided by 51 times. So in the current case, for the example above, our fin efficiency, sorry, did I say effectiveness again? So this is the fin efficiency. Is equal to 60%, or 0.6, saying that it is 60% as efficient as the fin that is made of the perfectly conductive material. All right, that wraps that up. At this point, you should have all of the information you need to solve that bigger problem on the homework. Last reminder that I moved the homework due date to Wednesday of next week, so it's not going to be due on Monday. And you all have a good weekend.